In this video, I'm going to teach you how to do the math relating to heating and cooling curves. This is an example of a heating curve for water. It shows the temperature changes that result as heat is added to solid ice. There are two major parts of this that you'll need to recognize for calculations. The first are the times when heat is being added and the temperature of the substance is increasing. During these times, you would use the formula to solve for the amount of heat required to raise the temperature of something, mass, specific heat, and then change in temperature. The other part that you'll notice is when the temperature is not changing as heat is being added. That's because that heat is going into phase changes during these parts of the graph. So in a phase change, you calculate your Q by either taking the mass and multiplying it by either the heat of fusion, which is specific to a certain substance, or up here as you go from a liquid to a gas, the mass times the heat of vaporization. So we'll be using these two formulas depending on what part of the graph we are working in throughout the next few problems. This graph is nice, though it doesn't have labels on it for a specific substance because it actually gives names to the phase changes. And so we want to make sure that you know the terminology of vaporization, condensation, melting, and freezing. So the first problem that I have for you is to calculate the amount of calories or heat needed to raise the temperature of 12 grams of water from 25 degrees Celsius to 45 degrees Celsius. So first you want to make sure that you recognize what the substance is and then which part of the graph are we actually on. So what you'll notice is we're going from 25 degrees, which is about here, to about 45 degrees. So we're only in this small section of the heating curve. Since that area of the curve represents a temperature change, we're just going to do a simple temperature change calculation, which is Q equals M, which is the mass, times C, which is the specific heat, times delta T, which is the change in temperature. So in this particular problem, if we plug in the mass as being 12 grams and the specific heat of liquid water, since we're in the liquid portion of the graph right here, we have to make sure we use the correct specific heat value. And then we're going to multiply by the temperature change, which is T final minus T initial. So in this particular case, the difference in temperature is about 20 degrees Celsius. You'll notice that I labeled all of my units, and you can see how nicely they cancel so that I'm left with units of heat, or Q, which is calories. So then when I plug in the math and I round to significant figures, I end up with 240 calories. In the next problem, like most of these problems, we're solving for Q. The amount of calories that are required to melt 5 grams of ice at 0 degrees Celsius and raise the temperature of the liquid water to 35 degrees. One of the things that you're going to notice is the importance of actually taking the time to map these problems out so that you know how many steps you will have to do in order to solve the problem. So first, we're going to notice that we're ice at 0 degrees. Well, where is that on the graph? And then we're going to liquid water at 35 degrees. So where is that on the graph? So the ice at 0 is at the beginning of the temperature change. So right at the beginning of phase change where the B is. Liquid water ending up at 35 degrees is somewhere in the vicinity of where I drew the dot. So we're in the middle of the liquid phase-ish. So we have to do two calculations. The first calculation is going to be a phase change as that ice melts. Then once it's fully melted, we're going to have to raise the temperature of that liquid water up to 35 degrees. So for the phase change calculation first, we're going to use Q equals the mass times the heat of fusion, because fusion is the process of melting. So I'm going to go ahead and plug in my mass as 5 grams and my heat of fusion for water, which is 80 calories per gram. My units cancel really nicely and I'm left with calories. And then when I round to sig figs, I have 400 calories. But the problem's not finished yet because I still have a temperature change. Right now we're liquid and we're right here. We're like a cold liquid, but we still have to heat it up to 35 degrees. So that last part is going to be doing the temperature change calculation, which I squeezed in at the bottom right here. So we're going to use Q equals MC delta T. We're going to put in the specific heat of liquid water. Make sure you have the correct specific heat value. And then the temperature change is 35 degrees because we're starting at 0 degrees down here and we're moving up to 35 degrees up here. So if we do the math, that works out to 175 calories total. So to complete the calculation, then we have to add those two steps together. It was 400 calories required for the phase change and 175 calories required for the temperature change. So total 575 calories. Okay, so moving on to the next question. Similar question, we're still working with water. This time we are going to vaporize 1,200 grams of water at the boiling point. Where is that on the graph? You need to make sure that you identify it's liquid water, so the phase change has not started yet and we're at the boiling point. So for water, that's 100 degrees. So we're going to have a phase change. Notice that they didn't mention anything about increasing the temperature of the water once the phase change is complete. So this is just a one-step problem. So we're going to take the mass of the water and we're going to multiply it by the heat of vaporization, which is considerably higher than the heat of fusion. That should make sense because all of the IMFs have to be broken and the molecules have to be separated by large distances in order to go from a liquid to a gas. Then I'm just going to go ahead and plug in my mass and my heat of vaporization. The units cancel nicely. I end up with 648,000 calories, which is, I'm only allowed 2 significant figures because of the 1,200. So I'm going to round it to 650,000. And then the question asked for kilocalories, so I'm going to do one last conversion. So it's 650 kilocalories as the final answer. Okay, next problem. We're still dealing with water, and we're supposed to calculate the Q when 18 grams of steam are condensed at 100 degrees Celsius, and the resulting water is frozen and cooled to negative 25 degrees Celsius. So we have a significant number of steps in this problem. First, we have to cool it through the phase change. We're going to condense it. Then we have to do a temperature change to go all the way down to the freezing point of water and freeze it solid. So it's a temperature change down to 0 and then a phase change to solid at 0. Then we have to cool it even further and we have to do another temperature change to cool it down to negative 25 degrees Celsius. So this is going to be a total of 4 steps in this problem. First a phase change, then a temperature change, then a phase change, then another temperature change. So I'm going to do each step separately. The first step that we're going to do is the phase change. So if I plug in all my values, the mass of the water is 18 grams, and we're going 540 calories per gram. One thing I should point out to you that's different from some of the other problems is we're actually going this direction, which means this heating curve is now being used as like a cooling curve. So we're cooling it. So if we say in the problem how much is released, then you can just use an absolute value in the calories. So let's write that down, absolute value. We don't have to worry about whether or not it's positive or negative. If we asked for the change, then it would need to be positive or negative. So anything going to the left is cooling, and that would be exothermic. That's the amount of heat that's released automatically going left to right, or right to left, excuse me. So I plug in my numbers and then I solved. I have 3 significant figures, so 9,720 calories. Next step is the temperature change. It's going all the way from the boiling point and we're cooling it down to the melting point. So it's the full 100 degrees Celsius. Make sure you use the correct specific heat for the correct phase of water, which is 1 calorie per gram degree Celsius. And so we end up with 1,800 calories for that temperature change. Next step is the phase change as we freeze the water. So it's the mass times the heat of fusion. The mass of the water is 18 grams and the heat of fusion is 80 calories per gram, so we end up with 1,440 calories, which is 3 significant figures. The last step is another temperature change. Be careful on the temperature changes. The specific heat values of water change depending on the phase, and most kids will put in this one automatically, and that is not the one you're supposed to use here. So be sure that you pay attention to which specific heat value you're using during these calculations. So we're going to use the specific heat of ice, which is 0.5 calories per gram degrees Celsius, and then we're cooling it all the way from the melting point of water, which is 0, all the way down to 25 degrees Celsius, negative 25 degrees Celsius. So total change would be 225 calories that would be required for that. So then all I did here was add together the previous 3 steps and then totaled it up, about 13,185 calories. We're not so concerned if the sig figs come out perfectly, since we didn't really teach you much about the adding or subtracting rules with significant figures. So as long as your answer is close to what's keyed out, that's perfectly acceptable. I saved this problem for last because it's extra tricky. Ethanol is probably one of the hardest type problems to do because of the melting point and the boiling point. They're seriously different than that of water, and the negative melting point makes things a little bit tricky for students when they are doing temperature changes that relate to the solid or the liquid. So I picked this one on purpose so that we can do some problems. So it's really important that you map out the problem before you start, and be sure that you label the melting points and the boiling points so you don't accidentally put in the values for water and get the whole problem wrong. Okay. So map it out before you start. It's number 1. Okay, so we're starting at negative 120, which should be down somewhere around there. And we are supposed to make it end up with a liquid at 57 degrees. So you can see I connected the dots. So we have 1, 2, 3 different steps that we have to add. 2 temperature changes and 1 phase change. Okay, so step 1 is a temperature change. We're going to use the formula Q equals mc delta T. I'm going to plug in the mass of the solid ethanol in this problem, which is 15 grams. Then I'm going to multiply by the specific heat of solid ethanol. Again, make sure that you're choosing the correct state based on what part of the heating curve you're in. Then we're going to calculate T final minus T initial, which is the delta T, and this is the one that gives kids such a hard time. So we're going all the way from negative 120 up to negative 117, so it's actually a difference of 3 degrees Celsius. So the total calories are not very much for this particular problem. It's only 10 calories, and really it's just 1 significant figure because of the 3 degrees Celsius. And again, that's based on adding rules, and you probably are unfamiliar with those, so that's why we're going to be a little lenient on the sig figs on these problems. Second step, we're going through the phase change, which is the mass times the heat of fusion for ethanol. So again, those 50 grams of solid ethanol are going to be melted when we add 24.9 calories per gram. And so to go through the phase change, we require 374 calories. In the final step, we have one more temperature change where we are going to go from negative 117 all the way up to 57 degrees. So make sure you use the correct specific heat value for the liquid portion of the phase, for liquid, and then go ahead and plug in your T final minus your T initial. So this is the one the kids usually mess up. So just make sure that you're taking the absolute value of the temperature difference, which is 174 degrees Celsius. So this is what my calculator spit out, but you know my calculator is not very smart. So I have to round it to significant figures. So if I round it to 3, it comes out to 1400 calories. In the very last step then, we're going to add all of the calories together to get the total amount of calories required for this transition of ethanol. So I put ish at the bottom so that you know that it doesn't really matter if it's exact as long as we can see all the work shown.